We have angle RPQ is 60 degrees. So that means that arc Q on circle omega is a 120-degree arc. If we have O as the center of circle omega, then angle ROQ is the central angle of that circle, and it's also 120 degrees. Let's apply the law of cosines to triangle ROQ, and a little AMC hack to keep your diagrams from getting cluttered is to redraw a simplified version of your diagram with just the important information. So here's triangle PQR again. And when we apply the law of cosines to triangle ROQ, we have that RQ squared is equal to OR squared plus OQ squared minus 2 times OR times OQ times the cosine of the angle between these two sides. Substituting, OR and OQ are both the radius of the circle, and angle ROQ is 120 degrees. Let's simplify and solve for R. And we get that the radius of circle omega is equal to 3. Next, we're going to draw segments from the center of circle gamma, which I'm calling G, to points Q, R, and O. Since that's going to clutter up my original diagram, I'm going to add it to my simplified diagram here. GQ and GR are both radii of circle gamma, so those have length 7. We have OR and OQ are both radii of circle omega, so those both have length 3. So we have triangle GRO is congruent to triangle GQO. Corresponding angles GOR and GOQ are congruent, and they add up to 360 along with this other angle ROQ, which was 120 degrees. That means their sum is 240 degrees, and because they're equal to each other, they are each equal to 120 degrees. Let's apply the law of cosines to triangle GOQ. We have GQ squared is equal to the square of GO plus the square of OQ, which is again the radius of circle omega, so that's the square of 3, minus 2 times the length GO times 3 times the cosine of angle GOQ, which we found is 120 degrees. We'll simplify and solve for GO. To make this easier, let's let x be equal to the length GO. And we'll factor the quadratic, which gives us a positive x, which is GO, and equal to 5. Returning to our original diagram, if I draw GO and it has length 5, I notice that if I draw OP, it'll be perpendicular to GP. Let me draw that off to the side. P is the point where circle omega is tangent to this side of the semicircle. So OP is perpendicular to GP. It's also the radius of circle omega, so it has length 3. And we just found that the distance from G to O is 5. So what we found here is a 3, 4, 5 right triangle. So what we're going to do is we're going to find the area of triangle PQR by finding the areas of 3 smaller triangles, QOR, POQ, and ROP off to the left. Let's start with the area of triangle QOR. We'll use the sine formula, 1/2 AB times the sine of the angle between these two segments. Substituting 1/2 OR times OQ times the sine of the included angle, 120 degrees. OR and OQ, again, are the radii of the circle omega, and they have length 3. So that's 9/2 times the sine of 120 degrees, which is root 3 over 2. So the area of our first triangle is 9 root 3 over 4. Let's take a look at triangle POQ. We'll apply the same formula since we know that OP and OQ are also radii of the circle. And we need to find the sine of this angle POQ. We know angle GOQ is 120 degrees, so we'll need to subtract angle GOP to find angle POQ. Let's just leave this area for now and go on to the area of the third triangle, triangle ROP. We'll use the same sine formula. So that's 9/2 times the sine of the angle ROP. ROP can be written as the sum of angle GOR and GOP. GOR, again, is 120 degrees. Here are the areas of our remaining 2 triangles. Let's add them. We'll factor out 9/2. Notice that For the formula for the sine of a difference, that's sine 120 cosine GOP minus cosine 120 sine GOP. Over here with the formula for the sine of a sum, we have sine 120 cosine GOP, and then it's plus cosine 120 sine GOP. For our first term, it's going to be the same for both of these two sines. So we have 2 times sine of 120 cosine of GOP. But then for the second terms, they're going to be opposite signs. Cosine 120 sine GOP minus and cosine 120 sine GOP plus. So those two will cancel out. We're left with 9 times the sine of 120 degrees, which is root 3 over 2. For the cosine of this angle GOP, we can return to our right triangle diagram. That's this angle over here, and the cosine is adjacent over hypotenuse, or 3/5. This comes out to 27 root 3 over 10. The area of triangle PQR is that plus the area we found earlier, 9 root 3 over 4, which was the area of triangle QOR. Finding a common denominator and adding, we get 99 root 3 over 20. The problem asks this to be given in the form a root b over c, and then it asks for a plus b plus c, and that's 122, or option D.